Hey y'all, it is going to be application day today. I may accidentally drop one or two new math ideas, but this is very much just supposed to be applying all of the matrix math that we've been learning for the last couple weeks to some application problems. So hopefully you find that enjoyable and not too stressful. We will in fact be looking at the stress tensor. We'll be representing three-dimensional stress and strain fields in matrix form and working with those matrix representations to do some problems in solid mechanics. So let's get to it before I strain the analogy any further. Heyo. Okay, sorry. Actually, no, I'm not sorry. Who are we kidding? Here it is. This is the stress tensor in matrix form. Boop. Well, show's over. That's all there is. 2-minute video. Or, maybe there's more to it. So we have these 9 elements here in this matrix way of writing out the three-dimensional stress. And to explain what those are, I have a picture. This figure has a lot going on, but it's actually very useful and very helpful once you unpack it. So here's how I want you to think about this. When we're looking at these stress fields distributed throughout a solid body, really at the end of the day, this is telling us about energy density and about forces being applied within the material in different directions at different places in the material. And in order to do calculations on this, what we do is we take our solid volume and break it up into a bunch of tiny little elements, normally cubes. And so what we're seeing here is one of those tiny little cubic elements. Imagine that this is one little bit, like a little cubic millimeter or something, of a much larger piece of a puzzle, like an engine block or an airplane wing. So we have this little cubical, like really it's a little dV, a little differential volume element in the solid. And when we want to analyze the stress, the reason we need 9 different components is that there are 3 different coordinate axes, 3 different pairs of faces that this cube has. And on each of those pairs of faces, there are 3 different directions where stresses can act. So when we look at the labeling here, this sigma 1, 1, that is the stress in the x direction on the x face of the cube. And then we have the stress 1, 2, so that's the stress on the x face of the cube pointed in the y direction. And then 1, 3 is the stress on the x face of the cube in the z direction. So for those of you who have done some solid mechanics, you might start to recognize that some of these are axial stresses and some of them are shear stresses, and that is absolutely correct. So the rest of the labeling goes on, this is the y face, and so it's the stress on the y face in the x direction, and the y face in the y direction, and the y face in the z direction, the stress on the z face in the x direction, the stress on the z face in the y direction, the stress on the z face in the z direction. Aren't we so glad I said all that? Let's move on. There is also a collection of strain elements as well, because the strain is 3-dimensional and has within each little finite volume, the displacement of that volume can be different directions on the different faces of the volume. So likewise, we're going to have 9 different elements to this collection of strain elements, and we'll write them as a 3x3 matrix again. So here is our strain tensor, and we have these 3 diagonal elements, xx, yy, zz, or zz, and those are the axial strains, and then we have these shear strains, which are the gammas. And you might be noticing the 0.5 and like, what's the deal with that? There wasn't a 0.5 in the other matrix. That's true. This is more of a convention thing of making different ways of writing the equations line up with each other and be consistent. So in this case, when we're thinking about the good old simple days when it was just, stress over strain is modulus or however you want to write it, and we were pretending these things were scalars, and it was just the engineering stress, which was a single number, and the elastic modulus, which was a single number, and the engineering strain, which was a single number, to relate that engineering strain to these particular strain components, then we need this factor of a half because we're going to end up adding them together. So that's why we have these 0.5s here. Okay. So we've seen stress. We have 9 stress components. We collect them in a 3x3 matrix. We have 9 strain components. We collect them in a 3x3 matrix. And so you might be like, oh, wow, are we also going to have some kind of 3-dimensional modulus that has 9 components and it's a 3x3 matrix? Well, if you're thinking ahead, then good work. The way elastic modulus, I just said a minute ago, the way it's defined in your intro MSE course or an intro physics course, intro ME course, whatever, is engineering stress over engineering strain. And it's just a scalar. It's a number over a number. Well, we've already seen that that's not going to fly here because you can't divide 2 matrices by each other. So like, all right, well, we'll just write it as multiplication. That's not a big deal. I'll say modulus times the strain is the stress. So what's so bad about that? Well, here's what's so bad about that. What's so bad about that is the 3-dimensional stress, like these 9 components of stress resolved in different directions, are not directly proportional to the strain. There can be angles between all of these different vectors. They don't just all have to be parallel to each other. And that means that the elastic modulus is not just a number, because it's not just a direct proportionality between one and the other, as we have shearing and twisting, torsion and all of that. There's more to it. So one example that you'll see in ME211 or MSE 420 is you can have axial stresses on a body that cause shear strain. So now we have this difference where the diagonal stress components, the axial components, are causing off-diagonal strain components. The off-diagonals are the shear components again. So how do you deal with this? And then it's back to, can we do this as a matrix multiplication thing? Well, it's complicated. The short answer is no. The long answer is yeah, kind of. Let me get into it. But the point I do want to make here is it is not just a direct proportionality. So we are going to need a collection of values, a set of different elastic modulus elements that will give us the right relationships between stress and strain in 3 dimensions. And the thing is, no, we actually cannot, if we're being very complete and fully rigorous and as correct as possible, it's not actually just possible to write this as a 3x3 matrix equation. This is actually, okay, this is bonus content. Like, this is not on the test for the next slide or two. I'll say when we're back on, this is on the test. Young's modulus, the elastic modulus in a material, is a rank 4 tensor. You're like, what does that mean? Stop saying weird shit. Well, fair enough. But what that means is that there are actually 4 different indices. When we are writing out these matrices, like the stress matrix, for example, you have 2 indices. You have rows and columns. And that gives you the arrangement, 3 rows, 3 columns. That gives you all 9 elements. And same with the strain. Well, the elastic modulus, Y, in its, Y is right, in its full glory, has 4 different indices. And like, we don't even have names for those things. Like, we normally say rows and columns when you have 2 indices, but then like, what do you call it past that? This is a 4-dimensional structure, and each of those 4 dimensions, the index can take on 3 different values, X or Y or Z. It's just an absolute beast. If you, if you go to grad school or take some graduate level courses at some point, you will have to deal with some of this tensor mechanics stuff, learning to do these sorts of multiplication where you have more than 2 indices. It is very much matrix math on steroids. It's pretty fun, actually. It's one of those things that's very satisfying once you see the patterns and things and you learn how to simplify stuff. And it can be a good time in that way that math is satisfying once you get it. I don't want to go too far off script, so we'll just leave that there. Tensors, super interesting. I have taught them in this class in the past, but I ended up taking them out just to spend more time on other stuff that is more critical in MSE, honestly. But if someone's curious about it, hit me up. We'll talk about it. I think it's cool stuff. So how do we deal with this without going full on four-dimensional madness, however many different elements that is? I can't even count that high. And we have basically two options that are popular that you'll see commonly in textbooks, classes, stuff like that. One is to change coordinates. This is what I'm just going to come right out and say is the smart approach. Work in a different coordinate system instead of XYZ. Work in a coordinate system where these matrices are simple, where they have a lot of zeros, and that's going to make all the math much easier to do. So this will be a change of basis. This will be finding a transformation for our coordinates that will let us write things instead of x, y's, and z's with a whole bunch of terms all over the place, write it in terms of three special directions, hint, in the material or in the solid where the problem is the simplest. If only we had a toolkit for finding special directions under transformations. So that's exactly what we're going to do here. We are going to switch to a coordinate system where the three coordinate vectors are the eigenvectors of the stress tensor. I call this the eigenbasis. I don't actually know for sure if that's a legitimate math term or not. I've used it before and people haven't corrected me on it, but I was never quite certain whether I was supposed to or whether they were just letting me get away with it. But I hope you get what I mean by that word at the very least. We're going to go to a basis. We're going to go to a coordinate system where instead of x vector, y vector, z vector, we're going to have eigenvector 1, eigenvector 2, eigenvector 3. And that is going to then, when we find the three eigenvalues of this stress tensor, this matrix form of the stress, those three eigenvalues will be the three principal stresses in those three special directions. So in this new coordinate system, this stress will become much, much simpler to write. It'll just be a diagonal matrix, eigenvalue 1, eigenvalue 2, eigenvalue 3. And again, implicitly, this is written in a coordinate system where our three coordinate vectors are the three eigenvectors of the full-on 9-component stress matrix. So that's how this goes. That's what our goal is. So in terms of applying this, what you do is you say, okay, I've got my collection of stress elements. I have my different axial and shear stresses. I am now going to find the eigenvectors and eigenvalues of that matrix. And then I'm going to do a coordinate transformation into my eigenvector basis or my eigenbasis of the system. And then in those coordinates, there's only three components of the stress: the component along the first principal axis, the component along the second principal axis, and the component along the third principal axis. Why do we do this? Well, the first application that I want to focus on, and this will absolutely show up on the homework, you will get practice with this, is there's a quantity called the von Mises stress. And the von Mises stress is this particular calculation. So it's calculated from this combination, this function of the three eigenvalues of the stress. And this particular combination has a really important and really useful physical meaning. This gives us the yield criterion for our material. If the von Mises stress, this combination of the three eigenvalues of this stress matrix, if the von Mises stress exceeds the yield strength, then yielding will occur. This is really great because this lets us do problems that are more sophisticated than just stress modulus strain, like engineering stress, engineering strain. We can start to look at things in a three-dimensional way and look at problems where the loading is not simple and where there are shears involved and things like this, and still have a toolkit for calculating a single number that will, at the end of the day, tell us about the material behavior, how it responds to the applied force. So this is great. I'm a big fan. Highly recommend. 10 out of 10. What is even better about the, well, I don't know about better. I said even better, so I must have meant it. From a math point of view, this quantity, the von Mises stress, this is what we call an invariant. This is a new idea, so I guess this is our new math idea for the day. When you are working with matrices, they will have certain properties. One property of a matrix that we've seen so far is its determinant. This is a number that captures the size scaling of transformations applied by that matrix, as we saw in previous classes. So that quantity, the determinant, is an invariant of the matrix. Even when you change your coordinates, the determinant doesn't change. The individual components of the matrix will look different in different coordinates, but that particular calculation does not vary. So we call it an invariant. It is truly a constant and is not dependent on the coordinates that we use. And that should seem reasonable physically because, again, the determinant tells you how much larger or smaller do shapes become when they are transformed by a matrix. And that bigness or smallness doesn't depend on the coordinates. It is a geometric property of the size of things in space, which does not depend on the particular numbers that you use to write down where stuff is. So that was an invariant that we met before, and I never even told you. But hey, now I have. So for stresses, the von Mises stress is also invariant. You can calculate it in any coordinate system you want, and you'll always get the same answer. So that means you may as well calculate it in the simplest possible coordinate system, which is the eigenbasis of the stress. Cool. Big stuff, big ideas, but also very practical. That is one of the things. I'm honestly not a mechanics fan. Like, I'm just going to be real. I was never into mechanics. I'm still not super stoked about it. I have to admit, though, it is a location, like mechanics as a field, as a topic, is a place where some really heady math and very, very practical, daily important stuff come together in one place. And for that, I got to say it's pretty okay. All right, so I said that was one option, was a coordinate change and doing this from an eigenvalues point of view. And that's great. I love it. The other thing that you can do is, instead of having this crazy 4-index multiplication with like what's 3 to the 4th power, 81 different components. Like, I don't want to multiply 81 different components. That sounds awful. What you can do, though, is you can collect like terms and reduce this to a much smaller number of calculations. And this is thanks to symmetries in the system, like the shear stress, the XZ shear stress is the opposite of the ZX shear stress. Or when you're looking at strains, similarly, there are relationships between these elements where they either equal each other or are negative of each other. So even though there's a ton of terms in the full-on like elastic modulus calculation, many of them are the same as each other. And so what we do is we distill this down to a form where we're only dealing with the unique independent components and not all the ones that are constrained and determined by each other. When you do that, you end up with 6 independent components. So we're taking this, instead of writing a 3x3 matrix, what we're saying is, well, when you only look at the independent components, there's 6 of them. So I'm going to write a vector, a stress vector that has 6 components, and they're the 6 listed here. So we have 3 axial stresses and 3 shear stresses. And then you can go back to vector matrix land and not have to deal with 4 indices and nonsense like that. It's not nonsense, but challenging calculations like that. So I am now going to skip all of the algebra. You'll learn it in your mechanics classes. Or maybe you won't, I don't know. So I skip all of the algebra, and here's what happens at the end of the day. This is our relationship between stress and strain. So the modulus matrix, I guess if you want to call it that, this whole beast, this is what relates the stress vector with its 6 independent components here to the strain vector with its 6 independent components. So I know this looks like a lot, but trust me, this is better than where we started, because where we started was something with 9 components, something with 81 components, and then something with 9 components. So taking it down to 6, 36, and 6, that is a big improvement. I hope you can see that. All right. So anyway, here it is. This will be on the homework. You'll get practice with it. When your materials are not isotropic, however, that's where it really gets wild. I'm not going to spend a lot of time with this. I just want to introduce the concept. If your material has different properties in different directions, so I'm not just talking about response to applied loads, but actually intrinsically the material itself is directional. In that case, I mean, there's more math to do because you have not just, you don't just have E, 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 E the whole way down, but you will actually have 9 different components that go in this top left corner, and you'll have 3 different components that go in this bottom right corner. So, I mean, that's just how it is. Again, if you do a graduate level mechanics course, you'll have to deal with this. For now, let's just say, what are some examples where this comes up, and then we'll call it a day. Well, here's my example. This is all over the place in composites. I'm not saying that composites are the only application of this stuff, but they're the first one that comes to mind. And they're such a big deal in real life. Think about all the composites around you. Everything from the wood that things like houses and furniture are made out of, like wood is actually a very anisotropic material, to like carbon fiber that makes up bikes and sports equipment, things like that, to the concrete that the entire engineered world is made out of, like concrete with rebar in it. It's one of the most produced materials, period. I think it's number 2, like production by weight out of everything that humans make is concrete, where number 1 is steel, or maybe I have those two backward. Like composites are no joke in terms of importance, and they have very directional properties. When you, like, I'm looking at one of my guitars right now, and it's got a carbon fiber fretboard, and this means that its acoustic properties are directional. The speed with which sound waves propagate through the guitar neck are different in one direction than the other. It's just all around you everywhere in your life. Uh, So, yeah, it's important. Now, how do we use this math to understand composites? It comes back to directionality. When you have materials that have different properties in different directions, you simply cannot describe those with a reasonable scalar equation. You could describe it with giant collections of many scalar equations, but it's much nicer to just write it as matrices and vectors to collect components that are related to each other and do some matrix math. So when we want to understand when a complicated shape will yield, like go back to the airplane wing that I mentioned a while ago, that's a really important problem, right? To say, hey, if I have this much lift force acting, and then I have the weight of the wing itself, and I have these stresses that are transmitted from the fuselage to the wing, and so now I have this very complex loading situation. I need to make sure that this wing is not going to exceed its elastic limit. I don't want it to deform permanently. I want it to flex and spring back. And so to be able to calculate the von Mises stress and compare that to the yield strength of your wing material, that's very important. All right. So I could actually go on about this for a while, but I won't. This is the only video for today, so I didn't feel bad making it a few minutes longer. Tomorrow we'll have 2 videos and they'll be broken up a little bit. So see you there.